Okay, hello and welcome back. In this video, we are starting our work on Chapter 10. Chapter 10 is called Analytic Geometry. You may have also heard the term conic sections that would apply to the same topics. So we're going to revisit some familiar geometric shapes on the XY Cartesian plane, but we'll be describing them using some new definitions, and we'll start today with the parabola. So you'll see what I mean in a moment. But first I just want to describe this idea of conic sections. So this term comes from looking at this interesting 3D object. So it's basically two cones stacked on top of each other in 3D space, two three-dimensional cones. And if we intersect a flat two-dimensional plane, oops, I was trying to erase this, a flat two-dimensional plane like what's shown as these blue rectangles. Imagine this is a flat plane intersecting these three-dimensional cones, and all of the points in which they intersect produces a few familiar shapes that we've seen before, depending on the orientation of the plane. So if the plane is flat, you can see it produces, as at intersection points, a circle. So we can get a circle from this kind of intersection. If the plane is tilted, if there's some kind of angle, it's slightly hard to see here, but it distorts the circle in a way that produces an ellipse. If we have the plane intersect one of the cones and go out the side, it kind of breaks it open. So in our third example, you can see it produces this parabola shape. So we've definitely seen those before. And then if we get a similar intersection, but it hits both the top and the bottom cones, you may have not yet worked with this shape, but we get something called a hyperbola. Kind of looks like two parabolas on top, upside down on each other. So hyperbola. So this is sort of the cast of characters of chapter 10, or at least the sections that we'll go through. Um, there isn't a separate section on circles. If you recall, we kind of started our discussion in this class with the derivation of the equation of the circle. So let's just quickly revisit that because it's going to use some similar language that we will see for our other definitions of our other objects. So let's just recall, how did we get the equation of a circle? So imagine we want to describe all of these points. And when we think of circles, we typically think of some center point and some radius. So some distance from that center point to any point on the circle. So I'll call this like point P. So we can call that x comma y. And if you remember, we called the center point h comma k. Those are the two letters typically used for a center point or maybe a vertex. We'll see that as well. And we've been doing this a lot in other perspectives, but we can create a right triangle. And if you remember, we described these two side lengths. The hypotenuse is r, our radius. So we have some center point at hk. We could have some random point on the circle, which we'll call x comma y. And our radius we'll just call r. So if we describe the two side lengths of this triangle, make it a little bit bigger here. hypotenuse is still r. Um, this horizontal distance should be x minus h. The vertical distance should be y minus k. So the difference between y and k to get that distance, and the difference between x and h to get this distance. So we can say by the Pythagorean theorem, x minus h squared plus y minus k squared should equal r squared. And this was our general equation for a circle. And this is also the distance formula. We're really finding the distance between this point h comma k and this point x comma y. And usually we would say distance being equal to the square root of x2 minus x1. In this case, it's x minus h squared plus y minus y1, or y2 minus y1, so y minus k squared. Same thing really, we're just taking the square root of both sides. But that gives us another perspective of the equation of the circle as all points x, y that are some constant distance away from a center point. And that's built into our definition. Any point, we're really just working with the distance formula. Any point is a set constant distance. In this case, r would be fixed at some value. So any point on the circle is some known constant distance away from the center point, or the set of all points that have that same distance away from the center. So why don't I describe it in that way? And describe a circle as the set of all points x, y that are a fixed distance away from the center. So that are a fixed distance r away from that center point hk. So I'm bringing this up because we'll use this similar kind of description of these other shapes that we're going to look at. So we're going to be exploring ellipses, parabolas, and hyperbolas. And we'll have a similar kind of statement of the set of all points that have some kind of fixed relationship. Maybe it's the sum of two distances, or the difference of two distances, or relationships between certain points called foci that we'll see, and other objects. So we have this relationship by some constant distances that will be a recurring theme. So we'll start today with the parabola. And we've worked with parabolas before, especially in college algebra. Graphs of, if you recall, graphs of quadratic equations show up as parabolas. But we'll see a different way of expressing them, a different way of building their formulas. So we'll start there. And we'll start with first parabolas that have a vertex at the origin. And by vertex, if you recall, we mean it's like the bottom point if it's facing upwards, this maximum point if it's facing downwards. But we'll also be looking at parabolas facing left or right as well. So we'll see how those are also described. But the vertex is always that point, in a sense, a point where it changes direction, or a minimum or a maximum point. Okay, let's first read their definition of a parabola. It'll look a little bit different from what we've seen before. So they say a parabola is the collection of all points in a plane that are the same distance from a fixed point f as they are from a fixed line D. So here's that kind of verbiage, this like all points are the same distance. In this case, they're saying they're the same distance from some point F, which we'll call the focus, and some fixed line D, which we'll call the directrix. And that's what they define here. F is the focus of the parabola, D is the directrix. As a result, the parabola is the set of all points for which this statement is true. And they're just saying this in more, just using this different kind of notation, but it's the distance from the focus to our point is equal to the distance from the point to the directrix. So let's draw a little picture just to visualize this. So imagine we have some parabola. Let's say it's upward facing. So something like this. And at least right now, we're saying that the vertex is at the origin. So the vertex is at the intersection of the x and y axes. So we'll call this, oops, this will be our vertex point. Right now, we're saying it will be at 0, 0. So the focus will be some distance away from the vertex. It'll be aligned with the vertex, but like inside the parabola. So we'll call this our focus point. The parabola always bends towards the focus. So we'll see different orientations. And these little diagrams up here on the top right, on the first image, the focus would be in here. The second, the focus would be in here. And the third, the focus would be over here. And the fourth, it would be over here. The parabola will always open towards the focus point. And then this distance between the vertex and the focus point we'll call A. So we'll use this letter for this distance. In this definition, it's saying that every point on this graph is the same distance from the focus point and this line called the directrix. So the directrix exists on the other side of the parabola, would be somewhere here. So imagine some, in this case, a horizontal line. I think I'll make it more solid, just so we can really see it. This is what we're calling the directrix. So this would be, if we're looking at the vertex point, that's a good like starting point as our example of having these distances be the same. The distance from the vertex to the focus should be the same distance from the vertex to the directrix. So I can also call this A. So if these were coordinate points and we're starting at the origin as our vertex, that means I could call this focus point 0, A. And that would make the equation of this directrix y equals negative A, because we're some A distance away below the origin at that point. But in general, the distances are the same for any point on the graph, so I can call this my general point. Call that P. So what this definition is saying from this perspective is that the distance from this point to our focus point should be the same distance from this point going straight down to the directrix. And it may not, it's probably a little bit skewed due to my scaling on the drawing, but these two distances should be the same. So we're describing a parabola as, we can write it out, the set of all points x comma y that are the same distance from a focus point, which we'll call F, and a line, which we'll call D for the directrix. So we still need an equation though. We still need a written form. And the equation will be different depending on the orientation of our parabola, if it's opening up or down or to the left or to the right. So let's try to build an equation, and let's take the version. They want us to build an equation of a parabola with a vertex at the origin and a focus at some distance to the right of the focus. Notice that's what they're saying here. The focus is at a comma 0, where a is greater than 0. So it's some location to the right. So let's try to visualize this. So that'll be our y and our x-axis. So it's saying we have a vertex at the origin. The focus point will be some distance, or at some point a comma 0. Let's just say, oops, that will be here. Call this point a comma 0. That'll be our focus. So that means the directrix line will be over here at negative a. So imagine some line over here. And that means that the parabola should open sideways towards the focus in this direction. Just a rough sketch. And we can imagine some random point on here, x comma y. So we can build our equation using that statement that those two distances should be the same. We should say that the distance from the focus to our point should be equal to the distance from our point to the directrix. So let's imagine we have our focus point, and if we were to draw a straight line to the directrix, this would exist at negative a comma y. The y value would be the same, but the x value would be over there with the line at negative a. So let's just set up two distance equations. I'll write that again over here. Distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. That's our distance formula. So let's use that 2 times here. On the left side, we're going from the focus to the point. So that distance would be the square root of, I can say x minus a squared plus y minus 0 squared, because our points are x, y, and a comma 0. And this should be equal to the distance from the point to the directrix. So that should be the square root of, I can say, in this case, x minus negative a. That'll be squared. So I'm looking at these 2 points now. Plus y minus y squared, since our 2 y values are just y. So these are both under square roots, meaning we can square both sides. So we can write them without the square roots, and let's simplify things a little bit. This looks like x minus a squared plus just y squared should equal, that'll become x plus a because of the double negative squared. And then y minus y squared, that'll just be 0. So let's expand out these squared factors and see what will cancel. On the left side, that should give us, we're squaring x minus a, should be x squared minus 2x times a, let me say 2ax, plus a squared. We still have that plus y squared, and then let's expand out the right side. That will be x squared, this time plus 2ax plus a squared. So notice what will cancel. We have x squared on both sides, that should subtract away. Also the a squareds should cancel. So let's leave the y squared on the left side. And then when we add the 2ax from the left side over to the right side, it'll become 4ax. And notice that's what they give us up here. So this is another way of describing a parabola. It'll always have this 4 in the equation, and this is specifically one that has a vertex at the origin. But you can essentially read where the focus will be, or at least you can see the distance from the vertex to the focus. That's how we'll define A. So maybe I should make a note. A is the distance from the vertex to the focus. So this equation describes a parabola with a vertex at the origin and it has a focus point a comma 0. One additional attribute that we didn't describe yet is something called the axis of symmetry. Parabolas are symmetric, and they're symmetric about the axis, which is the line going through their vertex. In this case, it's just the x-axis. Later on, these will be shifted around. So if you imagine the line going straight through the vertex, that is your axis of symmetry. So we'll use that term as well. In this previous example, it would have been the y-axis, a vertical line going through the vertex. This equation will be similar if it's facing up or down. We'll just see x and y swapped out. We'll see some examples with that. We'll first see a couple where we have y squared that makes the parabola open to the left or to the right. But let's start working with this new definition for a parabola, using the idea of a focus point and a directrix line. So in the first example, it wants us to write an equation of a parabola with a given vertex and a focus point. They tell us that the vertex is at the origin and the focus point is 3, 0. So that means we can start to try to sketch a graph. So our vertex will be at the origin. I can place it there. And our focus point is over here at 3, 0. So 1, 2, 3. Put it in red. This will be our focus. So that means this distance from the vertex to the focus is a distance of 3. You can read that from the coordinate point. So that gives us our A value. And this will open to the right. So we should follow that form, y squared equals 4 times a times x. And when it opens to the right like this, we'll take a as a positive number. If it was opening to the left, then our a would be negative 3 instead of positive 3. So let's plug everything in. We can say y squared should equal 4 times a times x. We're saying that a is 3, that distance from the vertex to the focus. So our equation should just be y squared equals 12x. So let's get some additional points in order to graph our line. And the common points that are used are above and below the focus, or if this was facing upward to the left or to the right. We can imagine what would be the points. This is going to open in some way like this, but what would be the points directly above and below the focus? If we know this focus point is at 3, 0. Well, that means we have an x value of 3. So let's just plug in 3 for x. And then find out what our associated y values should be. So I can say when x equals 3, y squared would equal 12 times 3 is 36. So when we take the square root, we can say y should equal plus or minus 6, square root of 36. So that means we have our vertex point, but we should also have the point positive 3, positive 6, and positive 3, negative 6. So let's place those. Positive 3, positive 6 is up here, and positive 3, negative 6. So I've noticed the homework questions will ask for these 2 points. And they give a special name for this line that connects the 2 points. This is called, in Latin, the latus rectum. So they'll ask for the 2 points on either edge of this. So in our case, we got 3, positive 6 and 3, negative 6. And then let's place our directrix here. Well, if the focus point is at 3, 0, the directrix will be the same distance, but on the other side of the vertex. So I could imagine over here at negative 3, we'll have our directrix line. And as an equation, that would be x equals negative 3. A vertical line will have x equals some number. Just imagine x is always negative 3 for any point on this line. And if it's a horizontal line, the equation will look like y equals some number. So it's got a little bit crowded. Let me scoot this over, at least make it more visually separated. This just wanted us to find the equation and graph. But you'll be asked often for these different attributes, like what is the equation of the directrix? What are these 2 additional points on the parabola? Or we could also be asked for the axis of symmetry, just to throw another attribute on here. Since it's facing right, it's going to be a horizontal line going through the vertex of the parabola. In this case, just the line y equals 0 for the x-axis. All right, let's start from the other direction where we're given an equation and they want us to analyze it. By analyze, they just mean like give all of the attributes. You see, analyze. That probably means to find the vertex, the focus, the directrix. We could also be asked for the axis of symmetry, or those two additional points on the parabola. So we're given y squared equals 8x. So it looks like our previous form. So I'm expecting some parabola opening to the right, most likely, because this is positive. If this was negative, that would tell me that it opens to the left. This will open to the right. The y squared tells me that it's some sideways parabola. But we want it in that form. The general form was y squared equals 4 times a times x. So let's just express this with a 4. This would be 4 times 2 times x. That tells us that our a value is equal to 2. That's this number here. That'll be our distance from the vertex to the focus point, and also the same distance to the directrix. And it's in this form, which also means that the vertex will be at the origin point. So let's start to list these out. I know that the vertex should be at 0, 0. The focus point, and we can even start to graph this too. It's helpful to get some kind of visual image. So vertex is at the origin. Our focus is a distance of 2 units away from the vertex. So this one will open to the right, and our focus should be over here at 2, 0. That means our directrix should be over there at -2. This will be the equation x equals -2. So I'll write that here. Our directrix x will equal -2. Let's get those additional points. So using our focus point, this is the point 2, 0. Let's see what happens whenever x is equal to +2. So I can say when x equals 2, our equation is y squared equals 8 times 2. So y squared equals 16. That means that y should be plus or minus 4, meaning we should go up 4 units from this focus point. 1, 2, 3, 4. And down 4 units. 1, 2, 3, 4. So we got some additional points. I can label this. This would be 2, 4, and 2, -4. What else can we add? We could add the axis of symmetry. In this case, it's opening to the right. The axis of symmetry is the line going through the vertex and the focus point. So that would just be the line y equals 0. Let me scoot this a little bit too. So when asked to analyze, we're basically going to list all of the attributes. The vertex, the focus, the directrix, maybe the axis of symmetry if they ask, and possibly some additional points on the graph. And then we have a graph of the vertex itself too, or a graph of the parabola. So we've just looked at ones that open horizontally to the right so far. If this was a negative x, we would see the same behavior but opening to the left. So the positive and negative can give you an idea of which direction it opens. But it can also open up or down. And let's just take a quick look. They do some summary tables here. This is still when the vertex is 0, 0. So we'll see later when we shift the vertex around. But we would see something like positive 4ax. So this is our first example. That's what we've been working with when the parabola opens to the right. The focus is to the right of the vertex. If it's negative, our vertex is still at the origin, but the parabola will open to the left and the focus will be to the left of the vertex. If we swap x and y, so this looks like x squared equals 4ay. So same setup. All of the same ideas will apply. The a value is still the distance from the vertex to the focus point. But now we're just looking above or below the focus. If a is positive, or if you see a positive number here, that means it's above, so the parabola will open upwards. And then if we have a negative, that will cause the parabola to open downwards. But this distance is still a, so this would still be the same distance a. So let's look at some upward and downward facing parabolas. So in example 3, we're given x squared equals negative 12y. So let's look at it with a 4 involved. This would be x squared should equal negative 4 times 3 times y. That'll give us the negative 12. So that tells us our a value is 3. And because it's negative, I will assume that this will open to open downward. The focus should be below the vertex. But let's start out listing some attributes. The vertex will be at 0, 0. The focus point will be at 0, comma, negative 3. So since we have x squared, we need to think above or below the vertex instead of to the left or to the right. So let's start to graph this too. Okay, let's place the vertex point at the origin. Focus will be below because it's negative and a distance of 3 units away. So that gives me my point 0, negative 3. So that should already tell me that the directrix should be up here at positive 3 going through y. That looks like y equals positive 3. So let's give the directrix. Now let's get a couple points. So in this case, since it's opening vertically, opening downwards, I'm looking at points to the left and to the right of the focus, meaning I'll keep y constant. When y is equal to negative 3, let's find out what x is equal to. So I'll do that up here. I can say when y equals negative 3, you would have x squared equals negative 12 times negative 3. That'll give us a positive 36. So x should equal plus or minus 6, meaning will be a distance of 6 to the left and to the right of the focus. So I can go positive 6, negative 3 would be 1 point. And then negative 6, negative 3 would be our other point. And then we can say the axis of symmetry, this is going to be this time the vertical line going through the vertex and the focus. In this case, it's the y-axis, or the line x equals 0. So we've got our attributes and our graph. I kind of build the graph at the same time that I'm listing the attributes. It's helpful for me to see things visually. But technically, once we have the a value, we can find things out even without seeing the graph yet. And so if that's more your style, you can see they describe how the a would relate to the focus point and the directrix in this table. I got this table from the text. All right, let's look at example 4. This time we're given some attributes and they want the equation. So we want the equation of a parabola with the focus point at 0, 4. And they tell us the directrix is the line y equals negative 4. So let's find out the other attributes and graph the equation. They don't tell us the vertex this time, but we'll be able to find out indirectly. So if our focus is at 0, 4, that means it's up here, 1, 2, 3, 4, on the y-axis. So I'm assuming some vertically opening parabola. And it says the directrix is at negative 4. 1, 2, 3, 4. So where should the vertex be? Well, the vertex is always in between the focus point and the directrix. It should have the same distance between the two. So this places it again at the origin, which goes along with our theme so far, but it may not necessarily be at the origin. But if you're just given the focus and the directrix, you can find essentially where they would meet. What's the point in between? So our vertex is at 0, 0. And this tells us that we're opening upward. It's going to open towards the focus point. And it's positioned vertically. It's opening upwards. So it should be in the form x squared equals positive 4 times a times y. And we know our a value is 4. So our equation should be x squared equals 4 times y, or 16y. If it was the same thing but flipped, opening downward, it would be negative 16y. Let's get our additional points. So based on the focus point, we have a y value of 4. So I can say when y equals positive 4, then x squared would equal 16 times 4. 16 times 4 is 64, which is 8 squared. That means x is plus or minus 8. So let's get some 1, 2, 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8. So that means I should have a point at 8, comma 4, and negative 8, 4. So something like this. All right, let's look at one more in this theme where we're given some information and we need to build the equation. So let's find the equation of a parabola with a vertex at the origin. So our vertex is at 0, 0. If its axis of symmetry is the x-axis, we'll just write that down. And the graph contains the point negative 1/2, comma 2. So notice this time we're not given the directrix or the focus point, we just know a point on the graph. Let's start to imagine, is this going to open left, right, up, or down? Well, the vertex is at 0, 0. It doesn't quite tell us yet. They say the axis of symmetry is the x-axis. So that means I should have some parabola that opens to the left or to the right. And it has the point negative 1/2, 2. So if I imagine negative 1/2, 2. Well, that's up in the second quadrant. It's like somewhere up here. So that means our focus point should be to the left. Yeah, we'll have some kind of left opening parabola. So let's keep that in mind. So what would that look like? Well, it's opening horizontally, so it will have a y squared instead of x squared. And if it opens to the left, that means I should have a negative here. Negative 4 times some value a times x, where a will tell me the distance from the origin, or from the vertex to our focus point. Well, since we have a point is an x value and a y value. We have the point negative 1/2, 2. That's a legit x and y combination, or a pairing. So let's just plug that in for x and y and solve for a. So I can say 2 squared equals negative 4 times a times negative 1/2. That tells me 4 is equal to negative 4 times negative 1/2 will give me a positive 2. 4 equals 2 times a. Divide both sides by 2, and that tells me a is equal to positive 2. So that means our focus point should be a distance of 2 units away from the vertex. and I know it should be to the left due to having this point. It has to open in that direction. So that should just be the point -2, 0. That'll be our focus. And we have an A value now as well. And this will also tell us where the directrix is. It should be a distance of 2 on the other side. So our equation should be y² equals -4 times 2 times x. So let's just combine those. -8x. The focus point we found to be -2, 0. The directrix, that will be the line x equals +2. And then let's get some additional points. We do already have that one point, but let's say if we're using our focus point, that gives us an x value of -2. So when x equals -2, we would get y² equals -8 times -2. So y² equals +16, meaning y is ±4. So a little bit out of my scale, but somewhere over here, we could have -2, +4, and -2, -4. Just a rough idea. And that's pretty in line with our previous point there too. So we got our equation and then our focus and directrix. Just throw the vertex in here too at 0, 0. So let's generalize this now to have a vertex anywhere. We've been anchoring it at the origin. So we want to basically shift it to some other location. So just to summarize, when we're at the origin, we have either y² equals 4ax, maybe it's positive or negative, or x² equals 4ay. So let's just define the vertex. I'll say let the vertex be the point h comma k. If you remember with our equation of a circle, we ended up, when we generalize it to have any center point, we had those x minus h and y minus k terms. So we'll see that same thing here. Basically, our x will replace with x minus h, and our y will replace with y minus k. So we can say y minus k squared will equal 4 times a times x minus h. So that would be one case where it's opening to the left or to the right. Or the other version would be x minus h squared equals 4 times a times y minus k. So now we'll be able to visually see where the vertex will be. And it'll follow the same, we'll see the same thing with the equation of the circle, where if something is positive in here, it would show up as negative in the vertex due to this minus. And if it's negative, it'll be positive. We'll see some examples. Just fixing my notes here. So we can say our vertex will be the point h comma k, and a is still the distance from the vertex to the focus. And it's also the distance from the vertex to the directrix. But these are the two that we'll want so far. And these are both showing a positive value. If it's negative, it'll just flip the parabola in the opposite direction. So the book gives you another summary table, relating everything now instead of from the origin being the vertex to some general point h comma k. So they have it set up here. So everything will be similar. For me, it's helpful just to see how things visually line up. But this gives you some little formulas for how the introduction of this more general vertex point will change how we'll describe the focus point, and where the directrix is located. But I think it's good just to see some examples. We'll just be relating things to the new vertex point. But we're still some distance of A, so we can just, in this first example, describe the focus as whatever our starting point is for our x value plus that A value. So we'll see that general theme. Let's see this first example. So they want us to find an equation of a parabola with this given vertex. This time the vertex is at negative 2, 3. And the focus point is at 0, 3. So let's just start to visualize this. So the vertex is at negative 2, positive 3. So we're somewhere over here. Let's call that negative 2, positive 3. And the focus is at 0, positive 3. So that means the focus will be here. So that means we should have some parabola that opens to the right. Here's our vertex, our focus point. So already from here, we can get this distance. We want this distance from the vertex to the focus. Well, that's a distance of 2 units. You can see going 2 spaces here. So that tells us our A value should be equal to 2. And knowing this, we can already get our directrix. It should be 2 units in the other direction. So that's over here at x equals negative 4. So if we're opening to the right, we should follow the form where y is squared, but this time we have a vertex point. So y minus k squared should equal, an opening to the right would make this positive 4 times a times x minus h. So let me just write this again. Our vertex is negative 2, 3. So that's our h, and 3 is our k. And our a value is positive 2. So let's just plug everything in. This would be y minus 3 squared will equal 4 times 2, so 8 times x minus negative 2. So this is what I mean by it will flip in sign. Like notice it's a positive 3 for our y value and it shows up as minus 3 here. And it's negative 2 for our x value and it shows up as plus 2. So the minus in the formula ends up flipping the sign. So there's our equation. If we were given this from the start, we could read the vertex point very easily just by looking at it, which is nice. Let's get our additional points so we can produce our graph. So in this case, it would be above or below the focus point. We're given a y value of 3. Well, actually, I want to consider where x is equal to 0. Yeah, because I want to be above or below that focus point. So the x value will be the same, and I'll get 2 y values. So I can say when x equals 0, we would get y minus 3 squared equals 8 times 0 plus 2. So that means y minus 3 squared will equal 16. Take the square root of both sides. Y minus 3 will equal plus or minus 4. So y should equal 3 plus or minus 4, meaning it will equal either 7 or negative 1. So that means we would have the point 0, negative 1 for that lower point, and then 0, 7. It's probably a little bit out of my range. 4, 5, 6. Let's say 7 is up here. Probably a little bit asymmetric, but not too bad. So the process is pretty much the same. We just have these new values that need to include our components of the vertex. Technically, we've been working with this where this was just 0 and 0 if the vertex was at the origin. All right, let's see another example here. So this time we're given something that looks a bit different. We have x squared plus 4x minus 4y equals 0. So we need to get this into a form that's recognizable. We saw a similar problem when we were looking at equations of circles, and if you remember, we turned it between different forms using completing the square. Completing the square is a way of taking something like this. We have x squared plus x to some first power, and we'd really like to have x plus or minus something squared as a single squared factor. So completing the square will introduce a number that will allow us to factor it in this way. So just to give a quick recap, to complete the square, you look at this, what we'll call the b term, stealing that from like a general quadratic, ax squared plus bx plus c. Basically the coefficient of the term that's to the first power. You take that number, divide it by 2, and then square the result. So 4 divided by 2 is 2. 2 squared is positive 4. So I'm going to take positive 4 and add it to both sides of the equation. I'll add it next to the 4x plus 4. We'll have the minus 4y. And I need to add it to the right side of the equation just to keep things balanced. Notice now this will factor into x plus 2 squared. We would get x plus 2 times x plus 2 if we were factoring that. two factors that multiply to 4 that add up to positive 4 are 2 and 2. So we get the same repeated factor producing this nice squared result, which is what we want. And we still have minus 4y equals 4. So it looks like we're going to get something in the form x minus h squared will equal 4a y minus k. So let's get our y term over to the other side. Let's add that 4y over. So we'll get x plus 2 squared will equal 4y plus 4. And then we can factor a 4 out on the right side. We'll get x plus 2 squared will equal 4 times y plus 1. Now it's in this form. We can read it as the equation of a parabola. Let's start to list some of its attributes. So we can say the vertex should be at the point -2, -1. So we flip the sign. It's a positive 2 here, it shows up as a -2. It's a positive 1 here, it shows up as a -1. I can see the a value is 1 because it's 4a in the formula. We already have the 4, so technically it's just multiplied by 1. So where should our focus and directrix be? Maybe it's helpful just to start to visualize this. We can plot our vertex point at -2, -1. Okay, -2, -1. So down here. X is squared, so that means this is going to open either up or down. And we have a positive value here, so that tells us it's going to open up. And if our a value is 1, that means our focus point should just be 1 unit above our vertex. That looks like the point -2, 0. And that means our directrix should be 1 unit below our vertex point. Scoot this out of the way. So this was -2, -1. So that makes this line y equals -2. We should have some upward-facing parabola. Here's our equation and some details about it. Let's get those 2 additional points. So based on our focus, it should have a constant y value of 0, and our 2 points should be to the left or to the right of it. So let's say when y equals 0, we will have x plus 2 squared will equal 4 times 0 plus 1, just 4 times 1. Take the square root of both sides, x will equal plus or x plus 2 will equal plus or minus 2. So that means x will equal -2 plus or minus 2, meaning it will either equal 0 for -2 plus 2 or -4 for -2 minus 2. So we should have a point 0, 0 and -4, 0. So something like this. And if we were asked for the axis of symmetry, now we're away from the axes themselves, the x and y axes. But it's still just the line going through the focus and the vertex point. So I could say the axis of symmetry, this would be the line x equals -2. So you can steal it from the focus point itself. All right, the last section just has some applied problems. I think we'll just have one example here. But it gives us a nice description on why the parabola is a useful mathematical object, especially in terms of some physics-based problems. So they say that parabolas occur in many applications. For example, suspension bridges have cables in the shape of parabolas. They also have a reflecting property that is used in applications. It says a parabola that is rotated about its axis of symmetry generates a surface called a paraboloid of revolution, kind of like a cup or like a satellite. I think that will be our example. Yeah, if you take a parabola and then rotate it around in 360 degrees, it carves out this shape, this paraboloid of revolution shape. It says if light or if any other emitting source is placed at the focus of the parabola, all the rays emanating from the light will reflect off the paraboloid in lines parallel to the axis of symmetry of the parabola. So that's like this searchlight example. They're saying if you put a light at the focus point, the light will reflect out and then be directed all in a unified direction. You can direct and focus light. Conversely, it says the rays of light that emanate from a distant source so that they are easily, essentially parallel. So they're coming from some distant source, say like a star. When these rays strike the surface of a parabolic mirror, whose axis of symmetry is parallel to these rays, they are reflected to a single point at the focus. So the light is entering this telescope, reflecting off a parabolic mirror, and it all gets reflected to this focus point, which they're then reflecting through to this eyepiece. So it concentrates all of the light beams that come through to a single point, which essentially magnifies things for us. So this principle is used in the design of some solar energy devices, satellite dishes, and the mirrors used in some types of telescopes. So let's see a problem involving some of these ideas. So it says a satellite dish is shaped like a paraboloid of revolution. We can view it as just like a flat parabola, like a slice. So maybe something like this, looking at like the side of a satellite dish. The signals that emanate from a satellite strike the surface of the dish and are reflected to a single point where the receiver is located. So as they mentioned before, if it's a parabola shape, anything coming in will be reflected towards some single point, which is the focus point. So this is where we want our receiver to be located. So they say if the dish is 8 feet across at its opening and 3 feet deep at its center, at what position should the receiver be placed? Let's draw another version. So we have some parabola. They're saying that it is 8 feet across its opening. So I can imagine this distance is 8 feet. And 3 feet deep at its center. So I can imagine 3 feet here. So where should the receiver be placed? It's basically asking where is the focus? So let's place this just on a XY plane. We can place the vertex wherever we want to. You can imagine the vertex would be here. So let's just say that that point is at the origin. So we can imagine some sideways facing parabola with a vertex at 0, 0. And so I could imagine if I'm going 3 units out to the right, that's our 3 feet. It should be, if I split this into 2 distances, this would be 4 feet, and then this would be 4 feet above and below the center. So that means I should have a point at 3, 4. 1, 2, 3, 4. So up here. And 3, -4. So here's our parabola again, but it'll just stop at these points. But up until then, it'll fully follow the form of a right-facing parabola. So I can label this as 3, 4 and 3, -4. So what do we have? We know we have a parabola because they tell us that's the shape. It opens right, just because we're saying, I mean, it can open in any direction. We're just formulating it as opening right. We know the vertex is at the origin. And we know we have some points. Let's say we have a point 3, 4. Well, that's enough to find out the equation of our parabola. If it's opening to the right, it should be in the form y squared equals 4 times a times x. So we have an x and y value. Let's just plug that in. Y is 4, so 4 squared should equal 4 times a times 3. That gives us 16 equals 12a. So let's solve for a. That means that a would equal 16 over 12. Dividing those both by 4, this would give us 4 over 3. And what is a? A is our distance from the vertex to our focus point. So that means our receiver should be a distance of 4/3 feet above this central point. So we can answer in those terms. But this is really all we needed here. So we can say the receiver should be 4/3 feet from the center. So introducing this idea of a focus point allows us to use parabolas in a lot of new applications, especially if we're dealing with reflections. Okay, so scroll back up here. So that'll be it for this section. We looked at parabolas with vertex at the origin. We made that more general, just to being at some point hk. And then we saw that one applied problem where we could solve it by creating the equation of a parabola. So we'll continue next time looking at ellipses and then finish with the hyperbola in the following video. But we're continuing this exploration of different conic sections, slices of these 3D cones, creating some familiar objects and maybe some we haven't seen yet. All right, that's it for this video, and I'll see you next time.